Good evening, everyone. My name is Mike Orison, and on behalf of the Department of Mathematics at Harvey Mudd College, it's a pleasure to welcome you to the 22nd Michael Moody Mathematics Lecture. This lecture series honors the legacy of Mike Moody, who was a cherished friend, mentor, and inspiration to our department. Mike was raised in an old Kentucky family with limited means. His parents valued education, but he knew that if he wanted to attend college, he would have to find his own way to get there and pay for it himself. And he did. He received his BA from the University of California, San Diego in 1975 with a double major in mathematics and chemical physics and a double minor in history and philosophy. Pursuing an interest in biological systems, he then earned his doctorate at the University of Chicago in 1979, writing an applied mathematics thesis in population genetics. Mike's first academic appointment was at Washington State University. In 1993, he was invited to spend a year at Harvey Mudd College, and within a few weeks, he knew he loved our small but ambitious school. Mike joined the college permanently in 1994 and became HMC's first Diana and Kenneth Johnson professor in 1996, the same year he was named chair of the Mathematics Department. During his time as chair from 1996 to 2002, Mike helped transform the department by hiring 8 new professors and expanding the faculty to 12. He sought people who would inspire students in the classroom and who had a passion for their mathematical work. At the time of his passing in January 2010, Mike was Vice President for Academic Affairs and founding Dean of Faculty at Olin College in Massachusetts. That spring, the HMC Alumni Association recognized Mike as an honorary alumnus in honor of his many contributions to the college. The Moody Lecture Series was created by the Department of Mathematics to celebrate Mike's legacy and his love for talks that reveal the joy, mystery, and relevance of mathematics. The series continues through the generosity of his family, friends, colleagues, and former students. And on behalf of Mike's family, I'd like to thank the entire math department and the HMC development team for their unwavering commitment and support for the series. And now, to introduce tonight's speaker, please welcome my colleague, Professor Francis Su.
All right, I am really pleased to be welcoming you tonight to hear Eddie Wu, who comes to us all the way from Sydney, Australia. Eddie is a high school math teacher, but he also has many other roles, which include working for the Department of Education in his state as an educational leader and as a professor of practice at the University of Sydney. And in both of those roles, he helps teachers think about their crafts and grow in their teaching. But I think most of you would probably know him from his YouTube math lessons, which he started in 2012 for the benefit of an ill student who could not attend in person. This is way before the pandemic, right? And he had the imagination to think about how to deliver this material to a student who couldn't be there. Now, that was in 2012. Now, more than a decade later, he has followers from around the world, nearly 2 million subscribers on his YouTube channel, which is also known as Wootube. I want to say a few personal comments. I first met Eddie in 2018. I married an Australian woman, and we were going to Australia on our honeymoon, okay? So I'm basically meeting a lot of my relatives, my Aussie relatives, for the very first time in person. And of course, they had no idea who I was, but when they found out that I knew Eddie, I suddenly had street cred. And Eddie was generous enough to invite me and my wife to both attend his his class at Cherrybrook High School, where I got to see him in action, and it was a wonderful, engaging lesson that even got my wife excited about polynomials, polyominoes, excuse me. And so I'm really pleased that you'll get a chance to hear him tonight. I've been in Sydney for the last 8 months, and over that time, we've gotten to know Eddie and his family quite well, and I can assure you that he's as kind and charitable and as great a teacher in person as he seems to be on YouTube. And so I invite you to give him a warm welcome to Harvey Mudd College.
Thank you so much, Francis, for what I can only describe as an excessively kind welcome. And thank you to all of you for coming here this evening. I always wonder, particularly as we move into the cooler months, you know, back in my home, they're moving into the warmer months, but for you, moving into the cooler months, coming out of an evening and deciding that this was something worth your time is a huge honor. So I want to make sure I respect that time, and I hope we're gonna have a bit of fun tonight, actually, as we explore what I've titled The Meaning and Meaningfulness of Mathematics. Now, firstly, I'm gonna wake up my clicker. There we go. I thought the best way to do this, because I always like to know where I'm headed when I'm listening to a talk, is that I would begin with a bit of an introduction by explaining my sort of personal connection to this whole landscape that I want to talk about, what mathematics means and how it's meaningful. When we talk about the meaning of mathematics, I would like to present, if you like, a sort of argument for one view of mathematics beside another. A narrow view of mathematics and a broad view of mathematics. There's a place for each, but I kind of want to advocate for the value of one in particular. Thirdly, and this is probably going to take up the bulk of our time, and I hope it's the place we're going to just have the most fun, I want to kind of give us a bit of a tour of meaningful mathematics. It's going to look a lot and feel a lot like making and finding connections, which so much of mathematics is about. It's a study of patterns and relationships. So we're going to dig deep into that. And then lastly, it's always important to conclude, for me, with implications. What does this mean for us? I am not a fan of just tickling my mind with new ideas unless they have implications for me. I can see, well, I'm going to do something differently in the future as a result. And I'm going to commend to all of us some of the things that we can do as we go out from this evening. So, intro, meaning, meaningfulness, and then we'll see what life should be different for all of us going out of here. Now, Francis already mentioned a little bit at the start, but it's important for me to tell you the story and do it in a visual way. I'm a teacher at heart, and this is a grade 12 class of mine from a little while ago. And for me, I've had the wonderful opportunity and privilege of speaking with a few of you throughout today. So I also want to thank Harvey Mudd for just being so welcoming to me, and also to the people who are here tonight who are not from Harvey Mudd. Thanks for coming on in. I love working with young people. And actually the time that I've gotten to spend here today with some of you in bigger and smaller groups, it's just reminded me, I'm trying to get off of jet lag still a little bit, it's reminded me of the sheer joy of having the influence on a person who's at a stage in their life when there is so much of their trajectory still ahead of them, and there are great opportunities to change that, make significant differences in the choices that you make. Right? I usually teach children about this size, but in Australia, I have the great joy and privilege sometimes of visiting smaller children. I'm secondary trained, but whenever I get to walk into a primary or an elementary school, it always delights me. You can even see on the faces of some of these children who I'm working with in regional New South Wales, there is a wonder and a curiosity that for all of us is part of what I think is still alive and drives us to love and to pursue more of mathematics. And by the way, just on that note, can I just, for a moment, even though for the vast majority of you, I mean, there are a few familiar faces, I've gotten to spend like an hour or two with some of you throughout the day, but for all of you who are here, I just want to praise and honor the fact that you, evidently, despite biology and neurochemistry, you have kept this part of you alive. I heard it once said that, schooling kind of beats out the curiosity out of us. I don't think that's actually mostly true. I think that, if you can imagine, right, does anyone here have in their family or have, close relationships with a 3 or a 4-year-old child? Does anyone have sort of someone in their orbit? Yeah, okay. Or at least you probably have at one stage. Can you imagine having the curiosity of a 3 or 4-year-old child everywhere you go, like you'd die of starvation because you didn't go anywhere to eat food, right? So it's actually a really important function of our brains as we develop, that we get into patterns and habits and we realize, okay, this is the way the world is. I don't need to keep being curious about it. I understand it. Move forward. But you, especially, delightfully, you've kept this young spark alive, just enough, hopefully, that you can still get by from day to day, but that curiosity remains. What a gift that is. Now, previously, when Francis was just speaking, he mentioned the fact that I wear a few hats in Australia. One of those hats is that because of a few different opportunities I've had, when a news program or a radio program wants to work out something about mathematics, for example, when there's, I don't know, a big lottery that's, hitting a jackpot of whatever number of tens of billions of dollars, right? And they always want to know, like, what are the chances? How can we understand this in terms that mere human beings can comprehend, right? I often get a call and they'll say, can you come on the show? Can you talk about this? Can you explain it, right? And this has been a great privilege, but it has also exposed me to the fact, in a really stark way, that I think all of you are familiar with, which is that mathematics to most people is meaningless. Mathematics to most people is sadly meaningless. I talked to a production manager on one of the TV shows that I went on once. It was a morning talk show, and they put an image much like this on the background. And I said, why have you put that there? And they said, we want to give an air of mystery. A part of me broke inside when that production manager said that. But I had this great sympathy for this person, right? Because really, that's what this is to them, right? These symbols, all the formulas and equations are completely inscrutable to them. Now, I hope, don't look at this too closely, by the way. I didn't design this image, and there are parts of it that leave a little bit to be desired, but as a whole, I know that most of you see great meaning in most of these symbols. You recognize them, you know where they came from, you know what they signify. But for most of our world, the world in which we live, the world which I think this college, among many, equips us to serve, this is meaningless. And to me, this is a problem. Right? So I kind of want to make a case for how to find what the meaning of mathematics is beyond just the symbols, or rather in and through the symbols. And to do that, I take inspiration from John Allen Paulos, or Paulos. I'm actually not sure how it's pronounced, but a friend of mine, his name is Carl Kruszelnicki. He's a science communicator in Australia, and we affectionately call him Dr. Carl. He often said, I love people who mispronounce things because that means they learn them through reading. So if you've ever mispronounced something, like you pronounced Euler, and then you're like, oh no, take heart, okay? That means you learned it by reading, so good on you, okay? Now, John said mathematics is no more computation than typing is literature. Now let's take a moment to pause on these very few pithy words and think about their genius and their meaning, right? So much of mathematics is shrouded in mystery, is invisible to most of our world, because they see what's on the surface. They see what's on the surface, and it's computation, it's algorithms, it's things that for them, they probably went through a process but didn't really comprehend, right? And equating these two things is as silly, is as sad as equating typing with literature. So how can we try and tease out what really is at the heart of mathematics and all the ordinary differential equations that you've been working on today? I'm going to try and make a case for what I think mathematics means. Paul Lockhart, he wrote this fantastic, what would you call it? It's an imaginative story, but sadly, it's actually not that imaginative. It represents reality. And what Lockhart was lamenting, if you can't quite read the script up there, is how the education system that we have, it sort of perpetuates this particular view of mathematics that John Allen Paulos was kind of, saying is a real tragedy, right? Now, I think that he puts this image out of children This is the way he actually starts his lament. If you've never read it before, by the way, there's my first piece of homework for you as a teacher. If you've never read it before, please go and read it. Absolutely worth your time, right? But he paints this image of children who are forced to learn music. That music is compulsory. And that, you know, in grade 6, we have them copying out musical staves and getting the notes. By the way, have a look at this classroom, right? What's the notable absence in a music classroom? Instruments, right? But they will show themselves worthy of using the instruments if they show themselves really, really good at using all of the symbols and notation and getting them exactly right. And of course, doing it under time pressure, right? Because why wouldn't you? Oh, by the way, do it individually, right? God forbid you'd make music together with other people. This idea of music education, which we find laughable, sadly is a lot like actually what mathematics education is mostly structured like. And many of you are here because you survived that gauntlet. Good for you, but can't we do better than that, right? Could we reimagine a world where, thankfully, music education is not like that? Could mathematics education be similarly better? Now, it's not just because I ate dinner, but I'd like to give you a culinary metaphor for how perhaps we could do this, right? I have this guilty pleasure of watching TV programs about food and about cooking. I partly think it's because my mum, who was an excellent chef, who passed away 20 years ago, but passed on to me a love of food and cooking. Please note, I do not say a skill in food and cooking, but I love food and cooking, which means that, you know, MasterChef, Jamie Oliver, all these shows, I love watching these. I think it kind of fills a hole in me that can't do those things, but loves watching other people do them, right? Now, one of the things I've learned from these shows is that one of the skills you need to master, if you want to be a great cook, if you want to be a master chef, is the different kinds of cuisines, right? Because cooking Italian food is quite different to cooking Chinese food, right? It's like a whole different set of skills and knowledge, which is different again to cooking India food, which is different again to cooking, okay, so I'll admit, when I searched up Californian food, I feel like California roll doesn't quite hit but anyway, that's where we're going, okay? Now, this is what I would call one big domain of knowledge, the cuisines, right? Different areas of the world, different kinds of knowledge required. But if you really want to be great at cooking, there's an entirely separate domain of knowledge that doesn't get nearly as much attention as the cuisines. Maybe you've got it in your mind if you're a great cook, but let me try and spell it out for you, right? I'm talking about the knowledge, the skill to handle a knife properly. I'm talking about the knowledge and skill to be able to control heat in a pan. This is the thing I think I'm really bad at because I have a poor sense of smell. The ability to taste as you go and then modify and say, this needs a bit more salt, a bit more paprika, whatever it happens to be. And then this is one that I got from the TV shows, right? Apparently we all eat with our eyes. So the ability to plate up successfully, right? Like this is a really important skill. Do you agree with me that no matter what cuisine it is that you are cooking, these skills over here are always at play? These are always important, whether you're cooking any different style of food, okay? Now, when we compare cuisines with, I guess, what you might call competencies, right? I want to advocate for mathematics, a meaning of mathematics that gives each of these equal weight. You're saying, Eddie, what do you mean each of these equal weight? This is about food. It's not about food. This has been an analogy the whole time, right? I want you to think about the cuisines of mathematics. I mean, we don't give them a sexy name like cuisines, we call them content areas, right? But these are areas of knowledge that they feel kind of distinct one to another. You don't master Indian food at the same time as mastering Japanese food. You move from one and then you start mastering another, right? Now just pause for a minute. Follow the analogy with me if you can. If there are cuisines in mathematics like geometry, statistics, algebra, topology, what would be the equivalent over here? What would you place on the right-hand side of the diagram? I'm pausing on this for a moment because I really don't want to rush into ruining this for you and give you an opportunity to think about it, because if you don't have an answer for what comes on the right-hand side, then number one, I will help you and I'll try and fill it in, but I'd like to humbly suggest that maybe, even if you've got a lot of mathematics under your belt, maybe what you've got under your belt is that thing over there on the left, the content. That's a great place to start. But these competencies, actually, your national curriculum calls them proficiencies. These are a thing which, no matter which mathematical cuisine you're cooking, you're using them over and over and over again. Let me try and use some generative AI to help you understand. Number one, national syllabus and curriculum documents talk about something called conceptual understanding. Conceptual understanding is about having insight into how something really works. It's about seeing past the surface and to recognize some underlying structure. And often it's that underlying structure which you realize, oh, these two things are the same thing, right? This hand and this feather and this fin underneath are actually identical. That's what conceptual understanding is about. Secondly, we talk about adaptive reasoning. I've put a stepladder here because reasoning is kind of like our way to progress from a mathematical foundation into how do I go next? How can I deduce and add to what I know? How do I add from these axioms? How do I add next step, put all the lemmas together and you end up somewhere new. Thirdly, we talk about problem solving. Now, I use this analogy a whole lot, but it wasn't original to me. Problem solving is a little bit like having a toolbox and you encounter a novel situation and you've never met this before. There's not a formula, there's not a prepackaged algorithm. What do I do here? It was the great George Polya who described problem solving as what you do when you don't know what to do. You reach into the toolbox and you try something. It's probably not going to work. But you tried something, you learned, and then you went again. Maybe you realized, oh, this tool is too big or it's too small, and you hone your strategy. That's what problem solving is all about. And then fourthly, communicating. Now, I spoke to a few of you earlier today about why you came here. And one of the things which I think is very common among us in the mathematical field is that we can do the first three pretty well, but then when it comes to actually getting ideas out of our heads into someone else's, I put a microphone and a paintbrush there because we use all the tools available to us, right? We draw, we speak, we write. Much like with the toolbox, I guess true communication isn't bound by a medium. It's about saying, what can I do? Anything in order to make the idea that's clear in my head, clear in yours as well. I almost got an image of Patrick Stewart to put here as Professor Charles Xavier, but then I realized I'm too old and you guys don't know the reference, so I just moved on. Okay, now I want to make sure that you understand there's a relationship between the left and the right-hand sides of that slide that I just showed you, right? They're not two separate things. And I gave this metaphor to a few people earlier today, so I apologize, but I did withhold from actually showing you the picture because I knew I was about to show you the picture. I think about all those things on the right-hand side, the proficiencies, I think about them as related to the content, the way that a vine is related to a trellis upon which it grows. Let me try and explain. All these things on the outside are what we were talking about before as the proficiencies. They grow up organically, they intertwine. You can't truly do one without doing any of the others as well. Here's the thing about a vine, and many of you have perhaps vines in your homes or you walk past one every day and it's growing. A vine needs something upon which to grow. You can't just say, I'm going to be a great problem solver today. You've got to be problem solving in a particular place, on a particular problem. It's got to be in integral calculus, or it's got to be in topology, or it's got to be on a frame. And this frame, it connects together. It's this interlocking web, but if it's just a frame, if it's just content, it's dead. It's alive when you have all of these proficiencies actually growing upon it. And I know it's not really fair of me to say this, but I'm just gonna go out on a limb on behalf of the mathematics faculty here and say, I think this vine growing in this trellis, this is what we dream for all of you. That you can become mathematicians who take hold of this and who are living and pulsing with mathematical energy. This is the image that I have in my head. I hope it's the one in yours as you amass more knowledge and develop more skill. This is the broad sense of mathematics I'm trying to advocate here for. I want you to not just think about, okay, I went through 4 years of college, I learned a bunch of things, right? I'm thinking about eigenvectors and I'm thinking about echelon operations on matrices. I can do that stuff, right? Great. But I hope you're using that for these reasons, that you have deep insight into why things are, that you can solve a problem you've never encountered before, because guess what? The world is full of those things, right? We want you to be equipped to go out into that world and have enough living mathematical energy to take on whatever you encounter. So, I mentioned before that I wasn't just going to tell you what I envision as my meaning of mathematics. I was going to try and hopefully help you see that mathematics is meaningful, and here's where we're going to transition into. I'm going to try and do something a bit meta here with you. I'm not just going to try and tell you about this. I'm going to try and do this with you. I'm going to try and, as the preacher Charles Spurgeon put it, light myself on fire and let you watch me aflame. We're going to do mathematics meaningfully together. And you don't have to do it like this. This is my way of doing it. And I'm a weird Australian person who's 16 hours out of whack, and I bring a very particular set of experiences to me to doing this. You can do this so much better than I can for the particular things that your unique experience equips you to be able to do. There'll be some things you look at me and think, man, I would never do it that way. Thank goodness, find your way of doing this. But I hope as we go through this, you'll see a vision, you'll catch a vision for making mathematics meaningful to all those people with whom you live and interact. Okay, let's start in an obvious place. You don't have to say it, but I do wonder how many of you are familiar with this name, Eugene Wigner, right? He's someone who is famous for talking about the meaningfulness of mathematics in a particular way. In some ways, you might say an obvious way, and that's why I want to start with him and then go and sort of expand my vision. Can I get a show of hands? Who recognizes that name? Oh, wow. Thank you for the people with the hands up. And that was much fewer than I expected it to be. So the rest of you are going to have some fun over the next 60 seconds. All right, let's think about Eugene and what he taught me. Eugene has this wonderful paper, which I'm going to give you the name of in a second so that you can Google it if you like, in which he writes, the miracle, mark that word by the way, the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics, that was the particular area that he was focused on. That miracle, it's a wonderful gift which we neither understand nor deserve. It's a gift, we don't really know where it comes from, we don't deserve it either, but what we should do is be grateful for it and hope that it'll remain valid, that it'll keep being useful in future research, and that it will extend for better or for worse to our pleasure, even though perhaps also to our bafflement in two wide branches of learning. This is the paper, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The point Eugene is trying to make here is mathematics is this incredible tool for understanding the natural world. Right? I remember the first time I discovered with such joy that conic sections, you guys learn about conic sections here? Yeah, you take the double ellipse, you cut it at different angles of orientation, and what that provides for us is the series of shapes that everything under the force of gravity, in R3 anyway, follows. Isn't that beautiful? Isn't it incredible that it does that, right? But why does it do that? Eugene's quote kind of reflects, it's like, wow, it's this incredible mystery to us, right? Now, we've come a long way since Wigner, and so actually it might be Wigner, but anyway, can't pronounce names. We have better understanding of that example as a single instance, but there are still lots of areas that we're delighted by, but we're baffled by the connection. Now, I'm using Eugene as a first example of the meaningfulness of mathematics because it's the obvious one, right? And that's why most of you who have or on your way to applied math degrees are doing something along these lines, right? You're applying fantastic math to some physical situations you like, or chemistry situations. We know the rules of how this works, right? I want to now, from the starting point, move right along to some places that might be more surprising to you, okay? Past things that are kind of like, yeah, this is a classic example. Okay, yes, this is another classic example. This one, a less classic example, because most people on the street they've seen snowflakes, they've seen Nautilus shells before, but they're less familiar with quantum mechanics. But nonetheless, this is what Eugene was talking about, right? This unreasonable effectiveness of complex matrix arithmetic to be able to describe the geometry of what we can see here, right? But I want to move past all that and tell you a story from where I come from. Francis mentioned that he and his wife got to come to my school, Cherrybrook Technology High School. I fully acknowledge that, having the name there in concrete makes it look slightly like a prison. I don't think that's intentional, but who knows? Cherrybrook Technology High School is, at least in Australian terms, a relatively large school. We have 2,000 students from grades 7 to 12. I realize that's sort of average size around here, but for Australia, which keep in mind is very sparsely populated, this is actually quite strange, okay? Now, a school of 2,000 means that there are about 135 teaching staff, and most of them sit in this one big staff room. Now, I don't know how many of you have ever sat or worked in an open plan environment like this. Some of you are nodding to me with faces that tell me you have PTSD from that experience, okay? Now, if you've never had that delightful experience before, let me explain why there are some people who are kind of like slowly rocking in their chairs right now, okay? An open plan environment is really good for some things, and it is terrible for other things. One of the examples of what it's terrible for is trying to concentrate on a task that's not that cognitively interesting when there's a really interesting, lively conversation happening nearby, okay? So let me tell you the story. This is from a few years back when I was relatively new in this school, of when this happened to me one day. It was coming toward the end of the first semester of a school year in Australia, which is, around May, June for us. And I was busily trying to write my grade 7 semester 1 reports. Now, you don't even have to be a teacher or educator of any kind to know that writing reports is not the most interesting thing to do. Please keep in mind, this is pre-ChatGPT. I had to type out every single one of those words manually. It wasn't fun, okay? Now, I'm sitting there trying to type away, and I overhear a conversation, maybe, I was about to say meters, about 20 feet away from me. Okay, so it's close enough for me to hear, and I recognize it's actually two of my art teacher colleagues who are having this conversation. Okay, without even looking, I can see that I can recognize that they're art teachers because I know their voices and I know they're having a conversation about something that's getting my attention. Okay, so I'm typing away, and it's not the volume of their conversation that keeps my attention; it's the vocabulary that they're using. Despite being two art teachers, they are using all of these mathematical words in their conversation, and that gets my attention. I think, that's strange, okay, but no big deal. It's probably, do you remember when you were at school, sometimes you would go on a camp, right? So teachers would go with you on your camp. That means those teachers couldn't teach their classes back at school. So they'd leave instructions behind for us teachers who didn't go to camp to go and cover. So I thought, maybe these art teachers picked up a math lesson and they were trying to make heads or tails of the instructions, right? That was my first theory. But the conversation was going way too long for them to just be trying to make sense of this grade 8 lesson and then move forward, okay? They were having a genuine, substantive conversation about this. So I thought, what's going on? They've been talking about math for a good 5 minutes at this point, and now I've made zero progress on this one report that I'm trying to write, okay? So after 6 or 7 minutes of this, my curiosity gets the better of me. I give up trying to write this report, so I stand up, I walk around the cubicle, and on their desk, I see this. Now, I'm going to confess that at this time, it was a few years back, I'd never seen an image like this before. I'd never seen an Islamic tiling pattern, the kind that you can find in mosques all around the world. And as you look at these images, you can probably guess some of the mathematical words that my art teacher colleagues were using, right? Words like tessellation, symmetry, reflection, rotation, polygons, and on and on and on, right? And as I looked at these images, after I got over being kind of arrested by the beauty of them, because they are beautiful, aren't they, right? After I'd got over that, I realized in sort of a flash, an instant, an epiphany, that these words, these ideas which I had taken as belonging to me, I was the math department chair, thank you very much. How dare these art teachers use my words, right? I realized that in fact these ideas do not belong to me. This language isn't just mine. These words belong to all of us. They're connected to things that I'd never dreamed of. They're meaningful to other people. This mathematics is meaningful to other people in ways that I'd never dreamed. And this experience a few years back, it kind of set me on a bit of a journey to think about where else might this be the case? Where might there be meaningful mathematics hiding in plain sight? For example, that art that you just saw before, Islamic artists have been doing this for centuries, literally, right? But if you come forward into more modern times, some of you might know the particular artist. You might recognize his style. This is an artwork done by Maurits Cornelius Escher, who was a Dutch graphic artist from the 20th century. This is Circle Limit 3. It's one of my favorites, and you can recognize the incredible mathematics that's underneath this, even though Escher would never have called himself a mathematician. If you come even further forward into time, this is a 3D printed lamp by an American artist. Her name is Barbara Grossman. And I just want you to take a moment to just admire, number one, the clear creativity it came to design this. It's all one piece, right? It's all contiguous. But number two, the mathematical ingenuity required to create such a design, right? That not only incorporates this sort of, marine theme, but also is just mathematically beautiful. And in fact, it's not just the visual arts that do this. Could I get a show of hands? How many people play a musical instrument here in the room? Yeah, okay, a whole lot of you. Thank you, hands down. So certainly those of you who raised your hands will recognize this image, but for those of you who don't, this is one visual representation of what we call the circle of fifths. I shouldn't say we really. I play the acoustic guitar, but my friends who are real musicians are very, very deliberate in saying, Eddie, don't put yourself in with us, like you're not a real guitarist, okay? But this particular diagram of the circle of fifths, it was drawn famously by who was arguably one of the world's greatest jazz musicians. This is John Coltrane, and what he was trying to represent there was the relationships between each of the different keys and how the major fifth, the sixth, each of the different chords relate to each other. We're going to come back to John Coltrane a little bit later on, but for me, it's just a fantastic representation of the fact that music is just the joy that people feel when they're counting but they don't know it. It's mathematical relationships made audible, right? Now, we know that music is made up of these predictable waves, right? But I love that we find sinusoidal waves everywhere if you know where to look. And this is an image, I believe it was taken in Israel, looking at the horizon at the same time every day as the year progressed. And is the geometry not beautiful? I defy you to find a single person for whom something like the sunset is not meaningful. And they don't know it has anything to do with mathematics. That's a tragedy that we can do something about. We have the knowledge, we have the tools, let's share that. Now, I'm going back towards Eugene, I admit, a little bit, but I can't not share this image because as a teacher, I work with a lot of teachers who focus on sport and physical education. And these are the first teachers to say, I don't do math, right? To which my response is, really? And I encourage all of you to think about, United States is probably very similar to Australia in being a somewhat sport-obsessed nation, particularly at certain times of the year. So let's take the opportunity to peel back the veil and reveal the mathematics that we enjoy every time we kick, we throw, we hit a ball, and to say, hey, the thing that you're appreciating here is actually deeply geometric in nature. But it's not just the geometry that tells the story. I'll pause for a minute as you have a look at this because I know there's a lot to take in. Some of you are smiling because you immediately recognize what this image is about, which is great, but for the rest of us, what you've got here is a representation of every point scored in the NBA since the 1997-1998 season in basketball, right? Up to 2019, 2020 anyhow. I do have more current data, but it doesn't fit so nicely on a rectangular slide, so I just stopped there, okay? Now, obviously, maybe not obviously, but clearly not all of those orange dots represent a shot. They actually represent several hundred or thousand shots actually. But there's a story here, a meaningful story that's told by the data. Quite a few stories actually, but let me just highlight one. Just have a look at these mid-range shots for a second. So if you can't quite recognize what's going on here, you've got the court from above, you've got the key in the middle, and then you've got the three-point line on the outside. So these are shots that are taken kind of from the sides of where the basket is, yeah? Now just have a look at those shots and then see how as time progresses, those shots kind of vanish and disappear, and they migrate to a place where there never were any shots 20 or 30 years ago. Now, some of you, as avid followers of basketball, know this is what they call the Steph Curry effect, because he opened up a whole new kind of play by being able to shoot not just from the three-point line, but as many of you know, from way back. And suddenly every team realized, whoa, there's a new weapon out there. What else can we do to try and challenge this? Because it's not just Steph Curry who does this anymore, right? Are you starting to get the threads together? Mathematics is meaningful to our entire world, to the people we live with who look at us and think, you math major, strange, unusual individual, good for you, but for me, I'm fine without all of those meaningless symbols, right? They're not meaningless if they can see the meaningfulness connected to them. Now, it's been, I really hope that this is not distracting for you or unhelpful, but I know because every time I open my mouth, you're like, oh, Australian, okay? I've tried my best not to say maths too much in your presence, but I know it sneaks out every now and then. The most iconic Australian building is this one, the Sydney Opera House. I hope all of you recognize it. It is a pretty famous building, even if you've never been to Australia. But I actually think the best view of this building is not this kind of aerial view. It's the view that I get when I go past it on a bus, whenever I'm headed from where I live, about an hour northwest of the CBD, and head over the Sydney Harbour Bridge, and this is what greets me, at least when there's nice weather, right? Look at this view, look at it really clearly, and I want you to pay close attention to it. This is why I'm staying on this image for a moment. I want you to pay close attention to the profile of the sails. Just look at those shapes. Even if you've never thought about this building ever before in your life, you probably recognize there is something mathematical about them. The question is, what is that mathematics? Well, I had the joy of partnering with the Sydney Opera House very recently, and I got to handle the original model that was used by Jorn Utzon, the architect, to design those sails. And that's why I'm wearing these funky gloves, because the Powerhouse Museum wouldn't let me touch these historic objects without some kind of protection, okay? Now, let's see if you start hearing this. If you don't, I'm just gonna do the narration. But what's most important is watch what I'm doing with my hands. Oh, it's playing down here. Okay, I'm gonna talk. Here's the top of a sphere, and it's been cut into pieces. One sphere with lots of different sections cut out of it, which I'm doing my best to arrange in a way that I've pre-memorized, and I had to try 10 times to get it right. Now, they're all abstracted from the shell of the same sphere. The reason why this is important is because Utzon won the tender for building, for the design of the Sydney Opera House long before he worked out how he would actually construct the thing. It just looks beautiful and striking, and he said, I'll work out the engineering later, right? But the problem with that is, you can't just make curves in whatever shape you like. It's fiendishly difficult to create, to design and manufacture everything. All of it was built on site at what we call Bennelong Point in Australia, right beside where the Sydney Opera House sits now. And the genius of the spherical solution, if my animation will work just right, is that a single sphere which has constant curvature and therefore each section is, in a sense, identical to every other section, can be built in longer or shorter combinations to create sails that look quite different to each other and give that striking image which I was asking you to look at really closely before. To me, as an Australian, this is deeply meaningful, and it's, I want to say, one of the purest mathematical things I have ever seen in my entire life. Even though I know, technically speaking, it's very applied, but I mean, it's a freaking sphere, guys. Come on, is it not delightful to see this? Now, I said before that we were going back to Escher, right? Actually, I said we were going to go back to John Coltrane, but I'm picking out Escher for a second because, skip a slide, sorry everyone. I want to get at this idea of how much he can show us the meaningfulness of mathematics to the world that we encounter all the time. Escher was very famous for his self-portraits. Back in the days before selfies, well, they're not before selfies. That was what selfies were. You just had to be mad wicked at art to be able to draw yourself, okay? Now look closely at this self-portrait. I'm actually going to zoom out. I'm going to show you the whole picture, okay? This one's called Three Spheres. No surprises for guessing why. Now, you can see there's this silver ball in the middle. And in the silver ball, by the way, you can see a reflection of three spheres, the artwork that he's drawing. And in the reflection, you can actually see the silver ball. That it's a bit meta. Try not to think about it too hard, okay? But pay close attention to the ceiling behind Escher's head. Can you see it there? Look closely. You can actually see there's a ceiling light dangling from the ceiling. Now, he's sitting in a totally normal rectangular room. But the ceiling behind him doesn't look totally normal and rectangular, does it? You recognize it as a rectangle, but you know it's not because, of course, that rectangle has been projected onto the surface of a sphere, and that curved surface deforms what you see, right? Now, this reality of projection, it's so delightful when you look at it closely and you see the way it distorts everything. This is a mathematical reality that's meaningful to every single person who's ever looked at a map. They may not realize it, and maybe you don't even realize it yet, but I'm going to try and unpack it for you. I love this particular map. There's so many different ones you can find around the world, but I love this one because it's made up of satellite photography, and you can see the terrain beautifully, and you can see the effect the equator has on different places. Particularly, you see sub-Saharan Africa just sort of shining out there very brilliantly, right? There's just one problem with this map of the world. It's not a map of the world. That's not what the world looks like, right? Of course, the world actually looks like this, but you don't get the map you saw before if you take this map and then just rip off the surface and lay it on a table. Do not recommend actually doing it, because if you do, you end up with this. You can see why, right? If you follow those meridian lines, north and south, they all meet at the north and south poles, which means they converge together. And that's why if we were to try and take a pair of scissors to that globe and then lay out what we got, you would have this strange kind of shape. Now, these gores are actually an accurate map of the world, but unfortunately, this is not very useful for map purposes, right? These gaps here, I mean, when Boris Johnson was talking about Brexit, I somehow think this is not what he meant, right? So what did cartographers do? What they did, sorry, was it too soon? I thought it's been a while. Anyway, what of course they did ingeniously was that they designed an equation that would map this into something that would fill all of those gaps and create a nice neat rectangle, right? Mercator was the name of the cartographer who created this particular projection, and the Mercator projection is the most common map that you will see around the world, okay? But think about what Mercator did. He took those gores from before and he stretched them out so that you don't see any gaps, right? Which creates an enormous problem. You can see it, can't you? Check out Antarctica. Wasn't that big the last time I looked, right? And in fact, everything is stretched and distorted in some way. The further from the equator, the more distorted it is. I don't know if any of you have seen this before, but this is really how big each of the nations on the map is. I'll give you a minute just to sort of take it in. As someone who lives in Australia, We're close enough to the equator that the distortion isn't that crazy, but certainly up here, when I look at Canada, I'm like, is that really what Canada's been this whole time? And of course, a country like Russia, so much of which lies within the Arctic Circle, it is deeply, deeply distorted. And let's not get even started about Greenland, right? So there are real issues in the way we look at the world and the way we think of it, that make this mathematics really meaningful, right? And when I say meaningful, I don't always mean that in a positive way. I think there are real problems that happen when we look at the world through a distorted lens and we just think that's what the world is. Mathematics is meaningful. We have to be really careful of the meaning that it can imply. There are other ways, of course, of projecting onto two dimensions, but that was just something I wanted to put out of curiosity. So now we've reached a point where I'm kind of sick of my own voice, and what I'd like for you to do is to experience this meaningfulness and this idea that mathematics is connected in places that we wouldn't expect. I would like you to experience it for yourselves, and that's why Francis so helpfully smuggled these pieces of paper and pencils into your seats. We're about to play a game called Sprouts. I'm expecting in a room of, unashamed nerds and geeks that some of you, many of you may have played this game before, and if you have, I expect you to be very good at it. But otherwise, I'm going to teach you the rules. You've all got a blank piece of paper, or many of you have a blank piece of paper. If you don't have one, you just need someone else nearby to have one. But for everyone who's got one on their hand right now, what I invite you to do is to draw 2 or 3 or 4, big fat dots on your page. And by the way, if you don't have a pencil or a piece of paper, please stick up your hand and Francis will very helpfully bring one around to you. Now, I said 2 or 3 or 4. I think 3 or 4 are probably the most fun number for you to play with. 5, you might not get out of here before they lock up the doors. So I think 3 or 4 is a nice number. I've only got 2 because this is just to illustrate for you the rules of the game, and then you're going to play. I'm gonna shut up and get out of your way, okay? So, once you've drawn 3 or 4 dots, can you do me a favor and hold up your piece of paper so I know when you're ready? Okay, great, fantastic. Thank you up the back. All right, hands down. So we're in a good spot. What I'm going to ask you to do is to make eye contact with one person nearby to you. So it could be the person you're sitting next to, or you might have to look behind or in front of you. You do need I was going to say a friend, but you're about to play a game that's competitive, so this person might not be your friend for very long, okay? You need a partner to play this game, okay? Now, once you have, and yes, please do shuffle along the seats if you want to get closer to someone so you can play with them. I'm going to walk you through the rules of the game, and you're going to start playing with me at the same time, okay? So this game is called Sprouts, remember? And the reason why it's called that is because every move of the game looks like this. You join 2 dots together, and on that line or curve that you just drew, you sprout a new dot. Join 2 dots, sprout a new one. That's every move. So whoever you want to designate is player 1 in your pair, can you please pick 2 dots on the page, join them up, and then sprout a new dot somewhere on that line. Would you do that for me? And then once you're done, hand it to your opponent. Opponent, once you've got the piece of paper, can you wave it at me so I know you're ready to go? Okay, we've got a few, fantastic. Thank you, okay, great. I love that there were a few people who they weren't waving because they were waiting for their player 1 to make a move. I'm like, don't overthink it. You don't even know 3/4 of the rules yet, so you don't know how to win yet. That's okay, all right? This is every move. You join 2 dots, you sprout a new one. Another rule you need to know is that as you continue doing this, so this is my orange player is player 2, okay? You can't keep doing this forever. There's a maximum number of lines that comes out of any given dot, and that maximum is 3. So I've got 4 dots on the screen right now. How many of them have reached their maximum? Exactly 1, right? It's the blue one in the middle, okay? So when this happens to you, because it will happen to you repeatedly, what I invite you to do is to put a cross through any dot that reaches a maximum of 3, okay? Player 2, go ahead and make a turn. If any lines get to, or any dots rather, get to 3 lines, put a cross, but you may not. There may be no crosses, it just depends on the moves that you make, okay? So join those 2 dots, and then sprout a new dot. Important not to forget the sprout, because that is what the game is named. Then you can hand it back. Okay, and you've gotten a handle on the basic play. Every move looks like this. You can join any dot to any dot so long as the lines don't cross and you keep to that maximum. Now, if you already crossed some lines, don't stress, this is kind of the practice game, okay? But watch carefully on the screen for a second. I said you can join any dot to any dot. You can even join a dot to itself, so long as you fit these rules that I've already mentioned. Maximum 3, lines can't cross, okay? Now, by the way, I probably should put another cross on, right? Which dot should I do? It's the, I love how so many of you are like, that one. That's mathematically rigorous communication if ever I saw it, okay? The black one on the right-hand side, okay? So I'll put a cross through there. All right, the final rule, and the most important one, because the one that tells you how to win, is that this cannot go on forever. Despite the fact that you are sprouting new dots constantly, you'll eventually reach a spot where you run out of dots, and whoever makes the last move will win. So you want to be the person to draw the last line. So to test if you really understand this, I'm going to finish this game on screen. I'm going to keep playing it, and I want you to tell me when the game is over, okay? So watch carefully, right? Here comes the next move. It's orange. Is the game over yet, or can I keep going? I can keep going, but should I put any crosses? How many? 2, right? 2, thank you. So there they go, all right? So here comes the next move. Blue goes there. Is the game over, or can I keep going? Okay, hold on a second. I've heard a few arguments now. Okay, so this is why the crosses are so helpful. This is why I encourage you to put crosses, right? When you put crosses where they belong, which is there, you realize that this blue dot over here has no other dots available. I already showed you, you can connect dots to themselves, but can I connect this one to itself? I cannot, because if you try, then you've got 4 lines coming out of that dot, you can count them. So that move's not on, okay? So let's go back. The blue player did that, no more moves available, blue wins, okay? You understand the rules of the game? You got a couple of pieces of paper there. I invite you to play a couple of games and see if you can work out a winning strategy. Good luck. All right, now I know I'm eyeing the clock and I recognize that I'm shortly to turn into a pumpkin, so I'm gonna try and speed along. Thank you for laughing. A lot of people are like, what is he talking about? I'm going to skip over a few things in my deck, so I apologize. One of the reasons why when I present, I always prefer to get out from behind there and come here is because, number one, I'm clearly hyperactive, but number two, I just want to be closer to you, but I am going to go back there in a second because I'm going to skip a few things and I can't do it with this, I've got to do it over there. However, before I do so, I love this game for so many reasons, right? Number one, I mean, it's just fun to play, especially when you win, right? But number two, even if you don't win, it spawns really interesting and powerful questions. For example, is this a fair game between player 1 and player 2? Chess, for example, is famously not a fair game because white, who goes first, has an enormous advantage over black, who goes second, right? Is this game fair? Don't know. Like when you were playing, did you feel like, oh, they got the first move, is that good? Or maybe I went first and I lost. Does that always happen, right? What effect does the number of dots have on whether one of the players has an advantage? I started with 2 dots. How many did you start with? Did it make any difference whether you started with a certain number and who perhaps might win? When you first started playing, I strongly suspect that you were just putting random lines anywhere, right? And you didn't know whether a move was a good move or whether it was a blunder, right? Is it random? Or are there strategies that make you think, I should go here and not there because otherwise this will happen and that's bad, right? And then lastly, because some of you are always going to ask this, right? If I have some arbitrary number of dots, can I then determine, is there a function for the number of dots that I'll finish with? Because I'll just go back for a second. I started with 2 dots and I ended with 7. Does that always happen? Or is there some variability? And if so, why is there? Now, I love this game because it has so many interesting questions, but I also love it because it wonderfully illustrates the meaningfulness of mathematics. Networks, of course, like the kind you've been making as you played this game, are found all around us. I'm about to use a network, hopefully successfully, to get to a different part of the States in the next few days so that I can have some other wonderful events like this. Of course, it's not just human beings. The natural world makes networks all the time. Ecologists, when they create a food chain, a food web, they literally track the calories as they move around from prey to predator, right? And it would be remiss of me not to point out the network that has governed our lives over the last few years. I always wondered how epidemiologists guided decision makers to say, you should do this, you should do that. Regardless of whether you agree with the decisions or not, there was mathematics underneath all of that. If there wasn't something as meaningful to our everyday lives than this, I don't know what it was. Now, the thing is, these examples I recognize, well, they're Harvey Mudd examples, aren't they? Because this is a STEM-focused college. You're like, of course, Eddie, of course you'd see mathematics as meaningful in these places. But the point I wanted to make to you was actually to surprise you with the fact that there are networks in all kinds of places you would not expect. Languages are related. Even individual words within a language are related and form a network. I said before that I was going to come back to John Coltrane. One of his most famous musical pieces called Giant Steps. It's a nightmare of jazz improvisation and it's awesome. One of the things it shows on his actual transcription of the music is you can see the different chord progressions. Those are the Roman numerals above some of the chords that you can see there, right? Now, those chord progressions, the particular ones here, like that 2, 5, 1 that you can see happening over and over again, it's a jazz progression. It's one of the things that makes music feel like jazz. But there are characteristic progressions for every genre of music. There are things that feel like pop and things that feel like country, and they often are not down to the instrument or the singer, it's the progression underneath. Now, I use this as an example of networks, right? Where's the network? Answer, it's staring you in the face. Those chords don't go to every other chord. They tend towards particular ones more than others. And you can map those relationships. And to me, that kind of network, which we feel every time we listen to a song, is so powerful. A bit heartbreaking. I'm going to have to skip like 9 slides here, but it's really important that you conclude. So, we've talked about the meaning of mathematics as not just the cuisines, which are cool, but alone aren't actually the thing that are really powerful and we can do things with, right? And that's why I introduced this idea of the proficiencies for you. Not introduced, I labeled it. I know you know them, but I want to give you language to describe them. I gave you a bunch of meaningful examples, not just meaningful to you, but to the people outside of this room, the people who would never come in this room with whom we interact constantly. Let's conclude. All of us, as we exit from here, will have something that we do with the knowledge that we have. I'd encourage you not just to think about what you do when you leave here as a profession, I encourage you to think of it also as a vocation. I love the word vocation. It gets a bit of a bad rap. Professions kind of sounds cooler, like I put it on a tie to say this word, right? But vocation just comes from the word voca, like vocal. It means what you've been called to. And you, by virtue of your knowledge, the gifts, the skill, the ability that you have been called to, well, numerous things. And I'm going to call you to 3 in particular. I want to call you to be an ambassador. I want to call you to be a symphony. And lastly, taking a note out of Mike's page here, I want to end on a more playful note and ask you to be a Stanley. Okay, let's look at them really quickly. Be an ambassador. This is actually a bit of a redundant, it's a bit tautologist because guess what? You are an ambassador. I don't know if you recognize this image. This is the UN General Council. And I've always wondered what it would be like to stand in this chamber and to represent my country, right? You represent the nation of mathematics every single day. When you go out into the world, when you interact with your loved ones, with friends, with strangers, you are the image of what math is to the people you know. Be a good one. Show them the meaningfulness of mathematics to them. Might take you a bit of time. I'm not saying like you instantly, hey, I'm ordering coffee from you, and by the way, mathematics, right? In fact, the best ambassadorial relationships are long-term. They're investments where you get to know someone and you realize that they're into music or sport or art, and then you can make it meaningful to them in that way. Be an ambassador. Secondly, be a symphony. One of the things I love about a symphony is that it's not a cacophony, right? Symphony literally means the sounds are together despite their diversity. This is such a wonderfully diverse room. It brings my heart joy to see how much diversity is in this room. And one of the things about diversity is that it gives us strength. I think about, sorry, I have to skip over another slide. Let's see if the camera is following me. I don't know who's on Zoom, but I hope you can still see me. We have not just linguistic diversity and cultural diversity. Even in math, the math itself is full of this beautiful diversity. And we are stronger through being different and being able to see connections that other people can't, and we lend that to each other. Be a symphony of mathematicians. And lastly, be a Stanley. I don't know if you're an Office fan. Stanley is a character who's known for facial expressions like this. He is a dour character. And famously, the only thing that makes Stanley happy is pretzel day. But the thing is, when Stanley's happy, Stanley is really happy. He is exuberant with joy, and this will be my final note to end on. To be an ambassador, to be a symphony, to make mathematics meaningful, remember what that joy is and shine it forth to the people who you interact. I'll give you this closing example. I'm often asked, like, what's my favorite piece of mathematics? And that's a bit like being asked, like, which is your favorite child? I have 3 children, right? And even if I do have a favorite child, I'm not meant to say which one. But if I had to say that a part of mathematics is my favorite, I think a leading contender would have to be geometry. Now, I know some of you are now looking at me like, really, Eddie? Really? Geometry? Well, let me make my case to you. In an equilateral triangle, the sum of the distances from any interior point to the 3 sides is equal to the altitude of the triangle. Okay, Eddie, why are you talking to us about geometry and showing us words? Just hold on, okay? Here's my equilateral triangle, and here's my interior point. The sum of the distances to the 3 sides, there are the distances to the 3 sides, okay? How can I show that the sum of the distances to the 3 sides equals the altitude of the triangle? Are you ready? Hold on to your hats. Let's put some equilateral triangles around those lengths. And now watch closely as I first rotate that one. And second, I rotate the top 2. And you did it. See, even those of you are like, geometry, okay? Is that not beautiful? Do you not feel the mathematical delight pulsing through your veins? I got some coffee. Okay, thank you so much, Yvonne. I appreciate that. Okay, my friends, I hope you've enjoyed experiencing the meaningfulness and meaning of mathematics with me tonight. Thank you so much for coming.
Eddie, Eddie? All right. Thank you so much for an absolutely riveting talk and a meaningful talk. I mean it. We have some time for questions. Professor Sue and I both have a microphone here. If you have a question for Eddie, just raise your hand and we'll bring you the microphone.
Oh, and please say your name, because I may have met you, and I've probably forgotten your name, but if I haven't met you, that would be even more helpful, so yes.
Hi, it's Caitlin. I was just wondering, you said that you had to skip like 9 slides. Could you take this opportunity to show us like one at least of those slides?
Okay,
you were
here I will,
excited about?
in fact, I will do, as any mathematician would, I am going to do exactly what you asked and nothing else. Here's what I'm going to do, and if you're curious about what the rest of the 9 slides after this were, then you can ask me. Here's the slide. This is what I was heartbroken to skip them too, but if you want to know, then come talk to me afterwards. Thanks, Caitlin. Okay, yeah, someone else. At the back there. Oh, in the front? Yeah.
Hello. My name is Will.
Hey, Will.
My question is, what do you think is the point of education, maybe more specifically secondary education? And follow-up question, what do you think your role as a secondary education teacher is to facilitate that?
Just a nice light question. Perfect. Okay. So what I'm going to do, Will, is to honor your question. I know in the scope of the time we've got, I'm only going to give you right now part of an answer. Okay. And please come and talk to me, and I'll give you some more detail. But yeah, like the sun would rise while I was still talking. If we, So I don't mean to sound like I'm dodging the question, but I truly believe this in my heart. There is not one point to secondary education because there are so many different stakeholders who invest in what secondary, in fact, all forms of education, but secondary education is the one I know best. And therefore, I know really well that there are not only multiple stakeholders, but those stakeholders have multiple mutually contradictory designs and intentions for what secondary education is for. We could talk about saying, let's help people get vocationally ready. Let's make them citizens who can understand the world and vote effectively if they want to vote. I could talk about, let's just make them whole human beings who are emotionally and mentally capable of contributing to their society. All of those things are true, but they all kind of tug at each other. And I don't think there is some kind of, this is the one purpose to rule them all. I don't think that actually exists because something like education is cared about by so many different people who are really different to each other and frankly sometimes fight with each other, that it would not be fair of me to say, this is the point, right? Not to mention the fact that, say, for example, in the education system that I'm responsible for, there are 800,000 students from so many different backgrounds and they're headed in so many different directions. And the point of school for each of them is a little bit different. I know this might sound a bit terrible, but it's number one, true. And number two, actually, if you can hold on to it for a second, it's actually delightfully powerful. Many of my students, academic success, for sure, was what I was hoping for them and working toward, and so were they, right? But I can think of, I'd need more than my fingers and toes, definitely, to count the number of students who, over my 16 years of being a teacher, actually the main purpose I was serving for them was, in secondary education, was keeping them alive. That was my goal. And I'm delighted that I can point to this number of people for whom I succeeded because of them being in secondary education. Now that's a very particular group of people. And I would never dream of saying, well, that's for everybody, right? For some of you, it's like, well, that's a given, okay? But for others, it is not. And I can't think of a higher goal for those people than that. You had a second point to the question, but I feel like I've already spent enough airtime on this. So why don't you come afterwards, Will? And I'd love to have a further chat. Thanks for your question.
Hi, thank you. That was great. This question is completely unrelated to the last one, totally different caliber. But I'm dying to know the answer to any of the Sprouts questions. Who tends to win? What are the strategies? How many nodes are there at the end? Do you know?
I've waited so long to be able to say this in a not entirely tongue-in-cheek way, but I believe the correct phrase to answer your question is, this is left as an exercise to the reader. I'm sorry, but I'm not that sorry. I'll be honest with you. I know answers to half of those questions, and I don't know answers to the other half, so yeah.
Hello. So the question is, how do you get kids interested in math? Because like when you talk to a student, you can be like excited and talk about all this like, wow, I can prove this thing from like two different sides and would have some background. But like I try talking to kids a few times, and sometimes they get interested, and sometimes just like, do I care? Like I don't. So like, can you give some piece of advice on like how you like share this like contagious feeling of joy about mathematics with like kids specifically?
Without a doubt. I'm going to give you kind of two answers to this question real quick. The first one is, don't be discouraged when you have this exuberance and joy and you're sharing it and it feels like it is like bouncing off and having no effect. Don't be discouraged because, I mean, you all were this at one stage in your life. It's like the job description of an adolescent to feel like unfazed and unaffected by everything around you and not show how cool it actually is, okay? And sometimes you must have a little bit of faith that actually that's worth continuing and it has an effect on them whether they're willing to admit it or not. So that's the first thing, don't be discouraged. Even if it seems like it's not having the effect that you want, stick in there. The second thing is, I'm going to quote my friend Francis, who himself was quoting, is it Simone Weil or Weil or Weil? Yeah, Weil. Who said, I'm going to get the quote wrong, but you can help me out, Francis. Every human being begs to be read differently. How'd I go, Francis? Cool, he's nodding. Thumbs up. Okay. I first encountered that quote in Mathematics for Human Flourishing, which if you have not read and you go here like, for shame, right? But what I think she was saying, every human being begs to be read differently. There's not one answer to that question. Every individual student who I encounter, there are categories of, what you want is the real world application. Like my student who was desperate to leave school and she wanted an application to her actual job that she was going to when she left school. Right? To others, I want to play. I'm not going to admit that I want to play, but actually play is the thing that I just want to have. I want to enjoy doing something without it having a reason that like, I'm going to solve a problem, right? Mathematics begins with just play, regardless of some real world context, which actually turns out to be a fake world context, right? And I could go on and on and on. There's even more reasons, right? Every human being begs to be read differently. You'll probably need to find and work that a little bit. But I will say, I wrote a whole book of the answers I gave to those questions that I got. So if you feel like my answer is a bit of a cop-out, lots of people have written about it and talked about it, and hopefully all those extra reasons will give you more tools in your toolbox to reach for. Does that make sense? Cool.
The public has these different misconceptions about math, such as, for example, focusing on the cuisines rather than the competencies, or not realizing how widespreadly math can be found in life outside of the classroom. And what can we, as STEM-focused individuals, do to help get rid of these misconceptions in a way that will help mathematical education in the future?
Was it Danny? Yes. Danny, what I love so much about what you just said, you may not have seen, there were some people, from where I'm standing, I can see everyone, and I could see some people nodding along as you asked, not just your question, but your follow-up question. Because the answer to your first question, like why is that so widespread, that's a really easy answer to that. They were trained. We trained them. Well, not we, like the royal we. People who know mathematics and who teach mathematics. I guess I'm more responsible for that than any of you personally, but that whole collective body has trained, sometimes unintentionally, frankly, but they've trained that mindset, right? And let's be kind for a second. I'll go right back to the start, right? If I showed you that diagram again, one of the reasons why that is the dominant thing that people have been trained to do is because that is much easier to train than that. That's super hard to develop, right? I can beat a child over the head with the quadratic formula until it's in their brain. They might not have any idea what it means or where it came from or why it's useful, but they'll know the quadratic formula. They'll have content in their head. Getting someone to the point of seeing something they never saw before, that's hard. Because in fact, what I'm trying to do is get their brain to do something, not my brain. And I don't have like marionette strings to go into their brain. I have to provide an environment in which those things can grow. It's a little bit more like gardening than lecturing. The plant does its own thing, but I create the space for it, right? And that's not easy with young people or with older people for that matter, right? So your second question, which was so important, what can we do, right? Well, I think the first thing is to be conscious of the fact that there are these two things. I had the great joy of talking with lots of people with great knowledge of mathematics, but when people talk to them, right, kind of this surface structure is what gets focused on. Because, you know, it's on the surface, right? If we all were mindful of the fact that when someone's like, whoa, you know differential calculus, or you know topology, or whatever it happens to be, and if we were to say, you know, thanks, or if it's like a thinly veiled insult, it's like, well, hold on for a second. Actually, the thing that I really do is I'm trying to learn how to solve problems that I've never met before. You do that all the time, don't you? You try. We want to be better at it. That's actually the skill that really matters to me. Or I want to clearly, in a persuasive and compelling way, communicate some reality to you. That's a thing you care about, isn't it? Everyone cares about that. And so that's part of why I was arguing for this broader sense in which we think of mathematics, because I'm persuaded that not everyone cares about the various different content areas of math. And I mean, the way you looked at me when I said geometry, not even mathematicians care about all the content areas in math. But these things, these are important to every human being. They're important to living in this world in a successful way. So that's what I encourage. And that's why I structured this talk the way that I did.
Eddie, thank you so much for such an inspirational and thought-provoking talk. If you have any additional questions, Eddie will be around after the talk here. But please join me in thanking Eddie for giving such a great talk.
Thanks, everyone. Thank you.